Let us begin our lecture The people that are now talking are probably going to be asking me questions about their grades, unless they hush. All right. We got some grading updates I'd like to go over with you, just so you know what the state of the situation is. The blooper on exam 2, clicking, that I had to regrade is finished regrading. Many of you did get additional points, which is nice. Okay, those are updated in web courses. The only exception, there's a handful of students that I have to grade their exams by hand again, and I'm going to be doing those this afternoon after class. So that's good. I've also started work on the bonus point code questions, and I hope to get those done tonight. And so still a little bit of pointage on the way. When that is in, then you'll be able to know what your exam average is for the first 2 midterms. And so basically what you have to do is add up your exam 1 and your exam 2 scores, and then divide by 100, and that'll give you your percentage. And if it's 90% or higher, then there's a good chance that I will ask you to become a special study group leader. And those will be going out this week, not today, but maybe by Thursday you'll have one. Okay? And if you get one, you have to respond by telling me yes or no. Now, nobody's required to say yes. If you want to say no, that's fine. We have 1 or 2 students every semester that say, no, I can't really fit into my schedule. I'm super booked up, and I can't do it, which is all right. Questions about any of that stuff? All right. Last announcement, exam-wise, is the following. 2 weeks from now, we have exam 3. The Thursday after that is the traditional Thanksgiving Day. Many of you, well, I shouldn't say many, perhaps I should say more than a handful have texted me in the messaging system of web courses that they have plane tickets to go home to wherever they're going, Schenectady, New York, or Dubuque, Iowa, or something like that, for Thanksgiving Day. And can they take the test early? Or can they take the test when they get back? Or can they take a makeup test? And the answer to that, all that is no. There's no early test, there's no late test, there's no makeup test, there's the test. And we published a schedule the first day of classes, and we've got to stick to that. And we've got 630 students taking exams all on the same day. So I'm not about to start letting anybody take exams late or early or any of that noise. Okay? And even the people that take exams over at the Student Accessibility Office, they take it at the same time we do. They're just over there at that different location. All right? And question? No, you may not. You may never do that. Yeah, you have to take it in this section, or you cause a big blob of bloop to be emitted into my exam grading world. And as you know, bloopers cause a lot of time delays, and so we want to avoid that. So yeah, definitely, if you're there's somebody in first hour that's been taking exams in this hour, but is no longer going to be doing that because her grade is going to be a 0 if she does it again. You're supposed to be in this section. You may not go to the morning section. And that applies for the final exam as well. You may not go to some of the other section final. You must come to this final. Any other questions? And you may be thinking to yourself, Dr. B is being a real SOB. And you are correct. I am an SOB, a son of a Brickner. But I also don't budge on exams. I mean, some things I budge on, like homework or exam bloopers, but exam schedule, never. Exam grading on the curve, never. Right? So we just can't do it. So don't ask questions about it, because I'm going to always say no. All right, I want to go through the mixing example from homework just for some extra reinforcement. And we're going to do a slightly different example, but we're going to talk our way through it. And then when you do homework 17 tonight, yes, there will be homework. I know you're sad and lonely if you don't have a nice big homework assignment. You're going to be seeing the mixing problem again. I'm going to give you another shot at it. We're going to do a lot of practice with that and with heat melt heat. So let's do this simple example together and go through the strategy. We won't solve it all the way down to the equilibrium, but you'll know the steps you must figure out in order to get the equilibrium temperature. All right? So let's say that we have two different substances, substance H, substance S, and substance H is at 333 Kelvin, so it's up there. It's the hotter substance. And substance S is a little cooler, 288. And let's say that there's no phase transition between those two temperatures for either of them. So they're going to stay liquids. All right? And the question is, how do you get the equilibrium temperature for this mixture of hot liquid and cold liquid? Because they're going to, the hot liquid is going to cool off a little bit, and the cool liquid is going to warm up a little bit, and they're eventually going to, reach an equilibrium temperature, and then they're going to finish the equilibration procedure or the equilibration process. Now, each substance has a different specific heat. So for instance, substance H, I decided with these two hypothetical substances, one of them has specific heat of 1.2 calories per gram Kelvin. That's substance H. And then substance S, I decided, all right, let's go with 1.4 calories per gram Kelvin. All right, that's not too bad. And I just said, well, let's just use some round numbers. I don't know if there's any substances with these specific heats. But what we do now with these Cinci specific heats, you can do with any other specific heats that actually are true and accurate. All right. Now, because they have specific heat differences, that means that if they gain or lose the same number of calories, their temperatures might be different, or the temperature changes might be different. Okay, gram for gram. And that's what specific heat tells you. So if you have a blob of substance S, it's going to be easier to cool down or heat up. And substance H is easier to cool down, easier to warm up, because it has a smaller specific heat. Substance S has a specific heat of 1.4, a little bit bigger. That means it needs, for every gram, it needs 1.4 calories to raise by 1 Kelvin. That's what specific he tells you. So it's a little harder to heat up. So calorie for calorie, gram for gram, you're going to have different delta T's. The other thing that happens is, what if they have different mass? What if you have a different size blob? So many grams for one, so a different number of grams for the other. All right, let's try that. Let's set up some nice round numbers for the mass. So we're going to use 40 grams for substance H and then 75 grams for substance S. All right? And we're going to inject that blob of substance H into the middle of substance S inside a container that's insulated, and then so no other heat comes into the system because it's insulated, but they'll eventually adjust temperatures till they hit the equilibrium temperature. All right? Now, because they have different masses, again, this is another reason where the same number of calories in or out might change the temperatures completely differently. You just don't know. You have to try it out for each one. But here's the thing that helps you figure out the equilibrium temperature. Whatever the hot substance loses is going to be absorbed by the cool substance, calorie for calorie. So if substance H, Omari, loses a calorie, the hot one, in its cooling off process, it doesn't have anywhere to go but substance S. So you're going to, calorie for calorie, it's not going to, it's not going to go to Helsinki, Finland. It's not going to go to Dubuque, Iowa. It's not even going to go to Chick-fil-A over by the bookstore and get a sandwich. It's not, it's just going to go right into substance S. That's it. Heat transport in this idealized problem. Now, a real-life problem, if you're working in a CSI lab, whoa. You might have a really small, instead of grams, you might have milligrams of a liquid that you've got to analyze. And they have fancy machines that can handle that and smaller samples. But for us, this is what we're going to do. So here's the question. If you have a calorie, 1 calorie, that substance H loses, how much does that change the temperature of substance H? What is delta T for substance H? So delta T, subscript H, there's your question. And what's the formula behind this? I haven't even mentioned any formulas yet till now. And I saw a discussion. Well, somebody was asking, well, what's the formula for number 13? And I posted there, I think for that discussion thread, a picture. My responses are limited. You must ask the right question. Because, okay. Look at the lecture notes. But I posted in there for some, I don't know who it was, but you have to ask the right question, and asking for the formula is not the right question. Talking your way through it, thinking your way through it, and grappling your way through it, that's what you've got to do. All right? So now, get your clickers out because we're going to do this question. And I hope you've typed down that information because you're going to need it for question 1. I have it set up for you in case you don't. But get your clicker turned on and get your brain on. And if you haven't been here in a week, hopefully you'll be able to remember how to operate your clicker, etc., etc. All right. And while you're doing that, my trusty assistant Darian is up here looking very studious. She's crushing some exam over here. It looks like, I don't know. Huh? She's going through her notes, getting ready to crush an exam. Okay, here's question 1. Frequency BB. What is the temperature change for substance S? Delta T subscript H. if it loses 1 calorie of heat. So Q is negative 1.00 cal. Right? And now down here in the lower right of the screen, you've got the specs that you need to figure that out. Oh, and by the way, the equation embedded in this, Q equals mc delta T, which in this case is the cool down equation. This is a cooling process for substance H. So go ahead and calculate that. And talk to your neighbor. Now it's nice to talk to your neighbor and consult and stuff, because your neighbor's responses are not limited. Did you ever see that movie, I, Robot? I, Robot with Will Smith? It's kind of scary, actually. It's like these robots taking over the entire United States, and only Will Smith can save the day. But it's kind of a cool movie, I, Robot. It's one of my favorites. Yeah. I have many favorite movies. But I, Robot is one of them. Actually, that's on the podcast. 30 seconds. But the scariest movie in my list of scary movies is actually a silent movie from Germany from like 1922 or something. Nosferatu.
Oh, okay.
Have you heard of that? Oh, it's like the Dracula story. Oh man, that's scary. And there's no sound. You know, so that makes it even scarier. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Uh-oh, we got some explaining to do. Actually, the correct answer is here, negative 0.02. And the bulk of you did answer that. Now, for those of you that answered A, which is about 11%, remember, you're losing energy, so you're cooling down. That means your temperature's decreasing. Delta T is a negative. So option A and option C cannot be the answer to this question. All right? Now, if you answered option C or option D, which is a fair number of you, about a quarter of the class, here's what you're actually looking at. You're looking at this quantity down here. Those two numbers multiplied together, 40 and 1.2, those work out to 48. All right? And, you know, that is nice, but that's not the answer. This is the way you calculate the answer. You solve for delta T. So that 48 calories per gram Kelvin goes into the denominator when you get delta T subscript H by itself. So go ahead and jot this last equation down. That's basically what you've got to figure out. Okay? And so if you crash and burn on C or D, know that this is the proper use of 48. Now, I'm going to ask you the same questions about substance K. So here are the specs for substance K. Excuse me, substance S. What is delta T subscript S? Serrano, did you see your, Mr. Serrano, did you see your change in grade? Yes. I was happy to see that. Because you were weren't you on the slacker list for that, for exam 2? Yeah. Now this is similar, but not exactly the same. So you're going over the lecture slides to improve your class notes? That means you get one of these. That's your standard trick, right? Yeah. What is it, chemistry? Yeah. Yeah. Most of it I'm good with, like the stuff we just started. And their notation, it doesn't appeal to me. I was working on that with my son over the summer, and some of the way that they did it, I thought, why are they doing it that way? It's not the way that I think it through. Yeah. But it's like translating from like Italian into Spanish. It's close, but not quite the same. Yeah. So, all right, you guys ready? 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Chit chat period over. Uh-oh. Looks like we got a bunch of geniuses in here. Good. Now, those of you, now look at this one. A bunch of you chose, not too many though, chose negative 0.00952. Okay, again, this one is a warm-up procedure for substance S, so delta T is going to be positive. So you shouldn't, option B and option D are verboten. You shouldn't even think about those two. But you guys did better, way better. And you know what that tells me? You're learning. See? I got you right where I want you. There's the calculation. If you did get it incorrect. If you didn't get it incorrect, go ahead and jot it down anyways. That's what you got to be able to do about a zillion times if you're trying to figure out equilibrium temperature. All right? Now, I've got a question for you concerning this delta T, and then, this should say delta T subscript S. I'm sorry, it says delta T subscript H. I forgot to change that subscript. This should be delta T subscript S equals the quotient, 1 calorie divided by 105 calories per Kelvin. Now, this plus the dip, the cool-off delta T, that means that every calorie that exchanges, you haven't gained or lost any energy, but your gap, your energy gap is narrowed. So you've narrowed the gap by 0.03036. And you might say to yourself, Dr. B, where did you get 0.03036? Well, it's 0.020833, I think it was, plus the delta T of the last one. You know, and one goes down, one goes up, and so the change, the net shrink down factor is 0.03036 Kelvin. So that's for a single calorie of exchange. Now here's another question for you. You still got your clickers ready? Every 1,000 calories, do it 1,000 times, you're going to have a different delta T. You're going to narrow the gap by quite a bit more. So here's your question. If you exchange 1,000 calorie, how big will the gap close, or by how many Kelvin will the gap close if you exchange a full 1,000? Okay? And you can go ahead and start voting on that question. And the reason for this, Sarah, is because to answer that, to kind of work your way through the equilibrium temperature, this is the kind of thing you got to think about. You know, you got to either think it over and then calculate, or think it over, calculate, think it over, calculate. You know, do a check. You know, you can make a table with this stuff and just easily work your way through to a solution. "30 seconds. And this answer is actually pretty easy. You don't have to do a lot of calculations if you think. Thinking is a big task. I hate those things. Leaf blowers. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. We got a lot of people with the right answer, 30.36. But those of you that over here in the yellow column, that's 4%, 7 students. Negative signs again. And those of you over here in the purple column, the maroon column, that's 13 of you. Option B is 0.03036 divided by 1,000. But that's not what you do for 1,000 calories of gain. You multiply. Just take whatever you get for 1 calorie, multiply by 1,000. Question?
I was a little confused with regards to the phrasing of the question. I wasn't sure if you were closing itself counted as a negative. Okay,
the question was up here in the front, it's a little bit confusing because if something's closing, shouldn't that be a negative number? And the answer to that is, the way I've stated it, it closes by 0.03036. That tells you how to use a positive, okay? If you follow my lead, and I do that on questions sometimes, tell me the drop distance, the number of meters, and don't worry about negative and positive. So follow my lead and you'll be all right. All right? And so positive all the way through. Now, here's the reason that we are working out all these decisions and all these little delta T's is on the problem you had for homework, this is your strategy. And you're going to have it again for homework this afternoon. Hopefully by supper time, if not sooner. You find your delta T's corresponding to a calorie plus or minus, or 1,000 calories plus or minus, and then you just keep doing that until you narrow the gap to 0. Question? Oh. Sorry. Thank you. All right, so you figure out your delta T. So you try it 1 calorie, and this, what we did was 1 calorie, and it's pretty small. And you've got 45 kelvins, and that only lowers it by 0.03 of a Kelvin. So you'd have about 1,500. Actually, it's kind of cool. 750. 1,500 calories roughly to equilibrate these two liquids. But anyways, do it by thousands. If thousands are too big, look at this, 30. 0.36, you're only going through 45 kelvins. So maybe go down to like 100 calories. That'll be every 3.036, and that's not too bad. You should be able, so 15 of those, so you'd have a table of temperatures, 15 levels on your table. Just work it out each time, and you're good. Because once you found delta T once, you just keep doing it again. Your cold temperature is going to inch upward, and your hot temperature is going to inch downward, and when they get to the same level, you're good. All right, now I want to do another question with you, and this is by way of reinforcing the other problem that I got some messaging from over the weekend. Students worried, what about that die-hard battery problem in the spring, in the delta Y? So I'd like you to try this problem again. And this is a hanging oscillator problem. A 4-kilogram block of chucktanium causes a spring to drop by delta Y equal to negative 0.20 meters. Figure the spring constant. And hit the refresh button, and you'll be able to type in your answer. And talk it over with your neighbors and see if you can get a number. And remember, the spring constant is a positive number. The negative sign is attached. Restoring force negative sign is in front of the K. So K is always a positive number. And the other negative sign in a spring force is maybe your delta X or your delta Y, which we have a delta Y negative in this case. So if you typed in a negative number for your answer, go back and change it to a positive. Very good. We're going to do the demonstration right after this. I'm going to explain why the negatives go away, but don't just willy-nilly ignore the negative sign, because sometimes you can't ignore it. Valeria, you're the only one on your row that's not giggling. Those other three characters over there are giggling. She's just over there calm as a cucumber. Very serious. Okay, 1 minute. I don't want it to go on the podcast. 30 seconds. Most everybody's done. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, you guys did pretty good on that. Let's just double check the reasoning. What we're going to do, so that you can be smarter than an engineering major, which admittedly is not difficult, but you want to be able to think a little bit more than, and we're in the engineering building, so I can't really say it too loudly, but you know, you want to be able to think a little bit more than those jokers do. So let's analyze the equilibrium position and look at the vertical forces in particular. All right? So here we go. I'm going to put a dot over here at the center of my block of chucktanium, and actually I'm going to actually move it out here to the right a little bit. And the first thing we know, at the center of mass, we have a dot, and there's a force acting on this block. Da, 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 da. Weight force. And we know how to calculate that. 4.0 kilograms, its mass, times good old negative 9.8 meters per second squared. And that works out to 39.2 newtons negative. And I'm using a negative sign here to indicate downward because we have another force, F equals minus kx, but it's an upward force. The spring pulls upward, so there's some newtons pulling straight upward. All right, that's the red arrow here. And we know how to deal with that. Let me get rid of my block here. Okay. First, we figure out the delta y. You know, 39.2 negative newtons pulls the spring downward. Here's the delta y. It's a downward pull. Delta y negative 0.20 meters. 20 centimeters downward. All right. That's normal. Depending on the spring. You know, a stiffer spring, it might be only 10 centimeters. A looser spring, 25. And that would be reflected in the spring constant, which is what we're trying to calculate. All right, so you have these two forces, and they're in opposite directions, so they add up to 0. Therefore, the net force is equal to 0. All right, here's one net force, negative k times delta y, and here the minus signs are significant. They're there for a reason. And negative 39.2 newtons with a negative sign, and that's added to my spring force over here. And supposedly, those two add up to 0 if it's equilibrium, the upward and the downward balance. Okay, so we have a fancy equation here. And I've got a minus sign. The k is going to be positive. Now, you may be saying to yourself, Dr. B, you've got negatives out the wazoo on this thing. All right? You guys are just having a good day back there. You're giggling the whole class. It's good. If I say the word shoehorn, you guys will probably start, see? You started breaking up back there. I don't know, a long weekend, huh? All right, anyways. So if you look at this, minus sign here, k is positive, delta y is negative. So I have negative times negative in this thing, so that's a positive. And this is a negative. All right, so that's good. So this thing here, when I put my numbers in, would come up positive, and then this would be a negative, and that's good because I got to add them up to 0. So everything's good if I keep my negative signs, organized. All right? And when you do that, the minus signs down. So I saw somebody in the back going like this. All right. All right, so this is your calculation down here. The minus signs, because look, if you take the negative 39.2 newtons to the right side and then divide by delta y, your negative signs cancel and you get a positive value for k. So everything looks copacetic, as we say. So 196, that is the Chuck Norris approved answer in newtons per meter. Okay, I want to do a demonstration with you now of some wave effects with Darien, RTA. Whoa, that thing's going to tip the tape. Okay. All right. And here, take this in. And what we're going to do is this coil spring here. So I'm going to continue the podcast, but you're going to view this. It won't be on the podcast. Kind of like a slinky, only a little bit smaller diameter. But, you know, it's flexible and it's easy to stretch. And, you know, kind of like a slinky. Okay, can you move back a little bit? Okay, and hold them. You're going to be the fixed endpoint. So Darien is going to be a fixed endpoint, and I'm going to move this. And what you're going to see are waves going to the left or going to the right on this, because that's what these springs are good for. Well, one of the things they're good for. Right now, let me squiggle. Let me get this. Okay, and I'm gonna. Can you step back just a little bit more? Okay, good. I'm gonna send one wave towards Darien. All right, now here it comes. Did you see that? All right, it heads towards Darien. And then it reflects as if she's sending the wave back to me. Now, she's not sending it, but she's reflecting it. Right? But it's as if she's another source of waves. All right? Now, let's watch it again. Let me try it again. Okay? Goes out to her, comes back to me, and then it just keeps ricocheting back and forth. All right. Now, watch what happens if I send a bunch of waves out. Right? If I send one out before it comes back to me, they're going to meet in the middle and interact. The fancy name for that is interference. Right? So let's see. Kind of boring, right? But if I send them out at just the right rate, watch what you get. I'm sending out waves. They're coming back from Darien, but it doesn't look like anything's moving left or right. Try to make a sketch of this. Make a sketch like a strobe photo, a bump and a dip. Because this is called the fundamental mode of waves on this spring at this distance. This is the fundamental mode. It oscillates between a bump and a dip if I wiggle the spring at exactly this rate. All right, so make a note of that. All right, now, and I'm going to ask you some clicker questions about this in a minute. But before we do that, I want to change the rate. I'm going to see if I can go a little bit faster and get the same thing. All right? You know, there's leftward waves going. There's rightward waves going. They meet, and if I'm doing it at the right rate, they're reflecting over there, they're reflecting here, and they bounce back and forth. But if you do it at just the right rate, just the right timing, you get that bump oscillating with the dip. Oh, did I say the word oscillate? Yeah. It's called a standing wave, what you just looked at. It doesn't seem to move anywhere. It just kind of stands there and oscillates. Now, let me see if I can get another one. All right. Oops. Oh, here we go. Look at this. Try to make a sketch of this quick before I lose it. We got one bump and one dip, or one dip and one bump. All right? So we got one over here oscillating between bump and dip, and one over, whoa, I messed it up. I can't do two things at once. And one over on Darien's side oscillating between a bump and a dip, alternately with the one on my side. Okay, so make a sketch of that. I'll try to get it again. Okay. And notice that until I get the right frequency of shaking, I don't. All right, there it is. All right, so try to sketch that. And you people with pencil and paper, you have the advantage today. Can't do this on a computer. Not the way you need to. All right, so what you're seeing there is called the first excited state. The first excited state. The first one you saw with just a bump oscillating with just a dip is called the fundamental mode. This one that you just saw, a bump and a dip oscillating with a dip and a bump, is called the first excited state. All right? That's the second one I just did. All right, now, next one. Next one. Here we go. Let's see if I can get another excited state, the second excited state. Now, do I have to go slower or faster? I have to go faster. So let's see if we can get the right. Okay, there's the first excited state. See, and I don't get anything until I get just the right. Whoa. Is that it? Yep. All right, there it is. And notice I'm going faster. My oscillation frequency is higher. And I have two bumps and a dip oscillating with two dips and a bump. Oh, I lost it. There it is. Whoop. I keep losing it. Dr. B. Let me try going faster. How about that? Third excited. Oh, did you see it? Third excited state. Let me try it again. You ready? Third excited state is going to be two dips, two bumps. Bump, dip, oscillating with dip, bump, bump. Now, let me see if I can get it again. It's tricky. I got it this morning. Let me see if I can get it again. There we go. Da, 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 da. All right. Whoa. Whew, my arms get tired. All right. So, students, just to here you go. Let's give Darian a hand. Let's review fundamental mode. A bump oscillating with a dip. First excited state. A bump and a dip oscillating with a dip and a bump. Second excited state. Two bumps and a dip oscillating with two dips and a bump, or a crest. Third excited state. Two bumps, two dips, oscillating with two dips, two bumps. All right? Now, I have a mental IQ test question, or as we say in the business, a public opinion survey. So I want you to answer the following question about the fundamental mode. And this one is written for Darian and my other TA, Nisha. And Nisha is in class right now, so she can't be here. So this is between Darian and Dr. B. You saw a standing wave looking like this snapshot. Therefore, the distance from where I was standing to where Darian is standing, the Dr. B. Darian distance is actually, and make a choice in terms of the wavelength of what you saw. This is basically a snapshot of one instant of time when you have the dip, or when you have the bump. "15 seconds. Now everybody's going to get a point on this because it's a survey type question, but I want you to make your best decision. And I love seeing everybody, there's like dozens of students going like this, you know, sometimes with both hands. It's very nice. 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Uh-oh. Well, you know, this is interesting. Look at this. Look at this distribution of answers. Hey, you guys, most of you got it right. The correct answer is half of a wavelength. A bunch of you, less than half of you voted for full wavelength. No, that's not a full wavelength. A full wavelength would be a full bump and then a full dip. And then at the end of that dip, you're starting on your next bump. All right? So that would be and this, so the fundamental wave, the distance, the physical distance from Darien to Dr. B is half a wavelength. And that is controlled by the stiffness of the spring and basically the distance between us, what the wavelength is. It is an example of a general phenomenon in waves called interference, and we're going to talk about interference today. First thing you need to know to have interference is you have to have two sources of waves. In other words, we had in this system up here in the front a secondary source of waves, which was Darien. They seemed to reflect, or they did reflect off here, and they propagated as if she were the source, just as if she were the source. And in fact, if I could mentally hypnotize Darien so that she would go at exactly the same frequency, she would have to hold her hand steady, and we could do it. But that would be very difficult to do. But I guess if you practice it, you could try it. I mean, not hypnotizing, but I mean, trying to, judge the other's frequency and stuff. Anyways, two sources of waves. They have to propagate independently. And at certain points, you might have two wave crests meeting. And if they meet crest to crest, you get a super big wave. Out in the ocean, that would be called a rogue wave. If you listen to the Discovery Channel or History Channel, sometimes they'll have a show about rogue waves and stuff, and the missing freighter of Atlantis and all this kind of stuff. Ships that have perished at sea because of rogue waves that we think. Now, the other thing is you could have two troughs that meet. And when you get two troughs that meet, then you get an extra deep part of the ocean, or an extra deep dip in the ocean, away from sea level. Now, for us, both of these points were right at the middle of the coil spring. That's when we had constructive interference. So here's your vocabulary term. When peak meets peak, when trough meets trough, you get constructive interference effects. They construct a bigger peak, a bigger crest. A good wave to surf down at Cocoa Beach, or wherever you have to go, or an extra deep part of the ocean. And if you've ever been in the ocean, you know that if you're in a small boat and you've got big waves and you're down at the bottom between two big waves, it can seem like there's two mountains to the left and right of you, and it's a little nervy. Now, if you get a crest and a trough meaning exactly the same point, guess what you get? No wave. It appears. And that is called destructive interference. If it were out in the open, it would be flat water. Okay, so where that rogue wave is, that's one of the reasons that rogue waves are so tricky. Because right near a rogue wave is flat water. And so you got this big trough, deep trough right in front of it, and right after the trough is a big crest, and so your ship goes into that trough, and it gets hit by a super crest, you're swamped, unless you can ride it out. Now I'm going to give you some sketches here of how constructive and destructive interference work in a very simple, one-dimensional example. Right? So think about two waves in the ocean. Now, these two images are photographs, or think of them as photographs, taken instants apart. On the left is wave A, it's propagating rightward. On the right is wave B, it's propagating leftward in the top image. A few seconds later, they meet. And where they meet, you have constructive interference. There's your rogue wave, if this were out in the ocean. The fancy term for this, at this location, at this instant of time, the two waves are in phase. Right? So write that down. The waves are in phase. When and where the waves are in phase, constructive interference. All right? Now this is for a peak, and we can produce waves in the ocean like this. It's not easy, but we can produce it. We can produce waves like this electromagnetically. Laser pulses we can make like this. It's not easy, but we can do it. Now, what happens after they interact? And write down A plus B, that second image, that's the interaction. That's the interference, the moment of interference. And it has to be constructive interference. Now, a moment later, they're moving off. They just keep going. They don't disappear. They don't destroy each other. They don't bounce off each other. Baseballs would have bounced off each other. You know. But B just keeps moving left. So now it's on the left side of the diagram and it's heading left. Wave A is on the right side of the diagram now and it's heading to the right. And it's just, you know, and that's kind of a cool thing. Baseballs never do that. BBs, bullets, particles do not do that. They'll ricochet off each other maybe, but they won't pass through each other. And that's because it's not a motion, a transport of water. Water is the medium in which these waves occur, but what's being transported is energy and momentum, and that doesn't get destroyed in this interaction. Now, let me show you destructive. Okay, destructive. So space down your page a little bit, flip to a new page, and write down destructive interference, one-dimensional example. All right, and unfortunately I can't do a three-dimensional example easily, but one-dimensional, yes. Okay, here's trough B propagating to the left from the right side of the diagram in the first image, and then crest A propagating to the right from the left side of the diagram. All right, now, where they interact, that would be zero amplitude, flat water. The fancy term here is they are out of phase. And really fancy terminology, you would say they're 180 degrees out of phase. You know, so it's like forward and back, up and down. You know, 180 degrees swing between one phase, the crest, and the other phase, which is a trough. That's 180 degrees of difference in phase. All right? Now, what happens to A and B after this moment of interaction? Flat water for just an instant, and then after that, here they are. They just keep pushing on. They keep trucking. Keep on trucking. You know, trough B just keeps going off to the left, and in a second it'll be out of view. Crest A keeps moving off to the right, and in a second it'll be out of view. All right. Now, one of the cool things is to try to visualize, anyways, two-dimensional, three-dimensional, and four-dimensional interference effects. And that is not easy to do. But one-dimensional is not too hard. And that's why the coil spring and the slinkies and stuff are very useful for demonstrating that. Now, I want to give you a one-dimensional example that is really important for you to know about. Wait a minute, question in the back. No? Okay. And that is this guy that I'm sure since everybody in here is a good, law-abiding citizen, you've never been ticketed by this guy. I'm not going to look at anybody, but I do have a confession to make. I got ticketed a couple years ago, 37 in a 25. And you know the worst part of it? It was the day that I finished final exams in May. And so, exam week, you're like 100% adrenaline 24/7 until you finish. And then all you can do is thinking about getting home, getting some sleep or some food or both. And that's what and I wasn't paying attention to the speedometer, and the cops nabbed me. Beats. This is how they get you. Beats. Now, a beat, you may think, Dr. B, what about these headphones? No, I'm not talking about headphones. I'm talking about a phenomenon called beats. Did we demonstrate that in class with the tuning forks, the first day of class? Okay, we'll try to do it on Thursday. There's a very nice demonstration of beats that we can do in here that's really nice. If you have two waves that are slightly different wavelength, then they're going to have constructive interference, but not everywhere. And this kind of blue line down here is the sum of the upper two waves. And you can see that there's constructive interference here, the lower curve on the left side, and then over here on the far right side. But in between, this is where you've got pretty close to destructive interference, flat water. All right, now here's a better set of diagrams for beats. So now this one I graphed up really carefully, very, very carefully. That other diagram is not very well drawn. So let's use this. This is my diagram. Go ahead and draw two waves, and if you look at these, they start out the same. They're in phase right up here. But out here, out here to the far right, they're starting to be out of phase. All right? And so I designed these two examples with very specific frequencies, wavelengths, and speeds. All right? Now, the first thing to identify is the equilibrium, sea level. If these were water waves, you can think of this line through the middle as the equilibrium. If it were sound waves, you would think of it as quiet. In other words, no sound. If it was electromagnetic waves, you would think of it as empty space, no radiation. So there's your equilibrium lines. And for this example, I decided, let me just use a nice round number for the meters for the speed. All right? So I said, all right, let me use 80 meters per second, and then let me set up some frequencies. So here's F1, 106.7 hertz, pretty low frequency, and then F2 is 119. Now, 119.5. The lower one in red is a little bit bigger frequency, so the wavelength is a little bit smaller. So make a note of that. A little bit smaller wavelength for the red curve, the second curve. Now, it might be hard for you to see that, but if you study the curves, especially if you go to YouTube and study the curves, you'll see that they're slightly out of sync. They're close, though, really close. Now, here's mathematically what you get when you add them together. This curve. Try to graph this one now. All right? You got a lot of big wiggles, because over here they're close to being in phase. But look right over here in the middle. Oh, man, look at this. Right in here, you've got red peak and a black trough. That's out of phase. So this is your flat water in here. All right? So this is the sum of the two in blue, thick blue line. All right? And this is what, if this were two audio sources, so one guy with a bass going in his car over here in one lane, and another guy with a bass going at a slightly different frequency in the other lane to your right, and you're right in the middle, this is what you'd actually hear. You'd hear these beats. All right, this is what you'd hear. In other words, this is loud here, this is faint, and this is loud over here. And these things are traveling left to right or right to left. So those loud parts of the wave are going to hit you, and then a faint, and then loud, and then faint, and loud, and faint. And it's going to hit you at a certain frequency. And the frequency is the difference between the two source frequencies. So F2 minus F1. Big minus little is the beat frequency. So in this case, it's 12.8. That's pretty easy. 12.8. So those loud, faint are going to come at you at 12.8 hertz, 12.8 times per second. Loud, faint, loud, faint. Now that you would not be able to register as a sound. If you're a little bit higher frequency, you would. But that's a little bit too low for audible sound. Your stomach would feel it. You know. Your skull would feel it. You know, your windows in your car would feel it. That's the frequency that your windows would be rattling. All right. Now, here are the wavelengths. At V equals 80 meters per second, the wavelength here is 0.75. The wavelength here, 0.67. And the wavelength down here is 6.25. How do I get that? V equals lambda F. 80 meters equals lambda times my frequency. My frequency is 12.8, therefore the wavelength has to be 6.25. And that's this distance, the distance between loud to loud. From loud past faint back to loud is 6.25 meters. And my wonderful students, that is how they nab you with a speed gun. They listen for the beats. I'm going to dismiss you, and we'll talk some more about beats on Thursday. Look for homework 17 by supper time tonight, if not sooner. You're dismissed.